In sections 1 through 5, we focused on univariate data, a single variable. What can we say about that? Well, quite a lot, actually. Here's one that we looked at. The ages of mothers who gave birth at a local hospital. We discussed the shape of the distribution. This one slightly skewed. We discussed percentiles, where the average was, roughly how spread out this was, and so on. And then we looked at the babies that these women had. And we said, well, let's look at the weights of these babies. They kind of look like a normal curve. Let's fit a normal curve and see where it does well and where it does poorly as an approximation. And that's all very informative. But one of the things that's missing in that discussion is any connection between the mother and her baby. We studied all the mothers and all the babies, but not which mother had which baby. And that's, of course, an interesting thing to look at. So that's what we're going to do for the rest of Stat 2.1x, is to look at the relation between two variables. And so now a unit is not an individual, it's a pair, mother and baby. And on each pair, we are going to measure two variables, mother's age and baby's weight. And so we have bivariate data, two variables, and we can represent the data in a scatter diagram or scatter plot, so-called because it's a scatter of points. And what is a scatter diagram? Well, it's what you would draw naturally. You have two axes. Along the horizontal axis, you have one of the variables, your choice which one you put there. And on the vertical axis, you have the other. So this point here, for example, this corner one, which is easy to identify, is a pair where the mother is just under 20 years old and the baby's weight is just over 70 ounces. And so each of these points corresponds to a mother-baby pair. And just looking at this, you can see that there's plenty of crowding around here, corresponding to the fact that most of the women were in their 20s. And something else that leaps out at me when I look at this picture is that, well, nothing leaps out at me. That is remarkable, because the variable on the horizontal axis is mother's age, and we hear quite a lot about, older mothers having more difficulty one way or another with childbirth. Certainly for this population of women, and there's more than 1,000 of them, for this population of women, the age does not seem to be very closely related to the weight of the baby that's being produced. For women in their mid-20s, the birth weights are from about 60 to about 170, as they are for women in their mid-30s. Now, of course, what's more interesting is a pair of variables where you can see that there is a relation between the two. There is a trend or a pattern in the scatter diagram, and that we will see by looking at a different kind of baby. These are baby birds. On the horizontal axis, I have the diameter of the egg, and on the vertical, the weight of the chick that hatches from the egg. Note, they're tiny. 6.5 grams is somewhere in the middle of the distribution. And what you can clearly see is an upward trend in the scatter diagram. And what does that imply? That implies that the larger the egg, the heavier the chick. In general. Not always, of course, because here is a point corresponding to an egg that was pretty heavy, but a bird that is relatively light. So we are not saying that every large egg produces a large bird, but by and large, that is what they do. Association is the technical term for any relation between variables. Positive association is what you see when the scatter diagram is sloping up. Above average values of one variable tend to go, in general, with above average values of the other. Linear, because if you look at the scatter diagram, it is not waving around like a snake. If I look through its center, there is kind of a straight line there. Which straight line, what does it do, we will identify later, but at the moment, just looking at that thing, it looks as though the points are roughly grouped around a straight line, not a curve. These terms we're going to see quite a lot of, so let's quickly review them. Association simply means any relation between variables. Positive association, as one gets large, so does the other. scatter diagram, you will see it sloping up. So we saw an example with the size of the egg and the size of the resulting bird. If you look at heights and weights of populations, those are typically positively associated. If you give the same set of students 2 tests, scores tend to be positively associated. And yes, you guessed it, there's negative association. That's when the scatter diagram slopes down. As one variable gets large, the other one gets small in general. An example of this is if you look at women in the United States, then educational level and number of children are negatively associated. The higher the educational level of the woman, in general, the fewer children she tends to have. A scatter diagram may be linear, there may be linear association, and that means the scatter diagram appears to be roughly clustered about a straight line, not something that has curves. The degree of clustering, how tightly clustered or how loosely, that we'll measure in the next section. But for now, we just have the general sense that if you look at a scatter diagram, you can shut your eyes and imagine a line going through it. What we're going to do now is look at your textbook, which has some wonderful applets for examining bivariate data. So here's a scatter plot of GMAT data. GMAT is a test that is taken by people wanting to go to graduate school in management. And there are many variables that can be plotted. What I have chosen to plot on the vertical axis is the first year GPA in the students' MBA programs, and on the horizontal axis the quantitative part of the GMAT test. Please ignore these numbers for now. I will tell you what they mean in just a moment. So the GMAT is a test taken by people wanting to enter MBA programs, and the data consists of 5 fairly strong schools. And so each point corresponds to a student, and okay, so now I put my cursor there, and you can see the x equals 29 and y equals 0.73. That one student had those scores, their GMAT score and their GPA are given by the x and the y. And that is why when I move my cursor around, I drive the program mad, because I'm not stopping at any particular point. This red point in here is called the point of averages. Its x-coordinate is the average of the GMAT scores, and its y-coordinate is the average of the GPAs. Now I'm looking at that distribution, and I'm seeing no particular trend or pattern. I'm seeing no particular relation between the quantitative GMAT score and the first year MBA GPA. It's clearly there are other variables that go into the MBA GPA than just the quantitative GMAT. Now you can change these variables. So I can look at verbal GMAT, and well, similar to the quantitative, there's no strong trend that is visible. The graph is pretty much horizontal. Just to be different, why don't we see what happens when we plot first year MBA GPA versus itself? Bang, straight line. X equals Y line. This is not a graph that you would normally look at for statistical analysis purposes, but I was just going to point out that you can plot a variable against itself and you will always get the X equals Y line. I looked through and I did not see any of these variables by itself having a very strong effect on the MBA GPA or having a strong relationship with the MBA GPA. What kind of graph would show a relationship? Well, let's see. Here we go. Linear association, you've seen that before. Please note that we're not paying attention to what's along the 2 axes. You can say a lot about the relation between the two variables by just looking at the rough shape. I feel so bad for this program when I move my cursor around like this. This part goes crazy. But back to work. Just by looking at the rough shape of the scatter diagram, you can see how these data are distributed. That is a scatter diagram that is sloping up. The association is positive. It is linear because I can kind of see a straight line roughly going through there. It's not curving. Football shaped. Now, in an international course, I have to explain this because it drove me mad when I first started studying statistics at Berkeley. Where I grew up, football is round, and so it is in most parts of the world. But in the United States, a football is an oval, so that is what is meant by football shaped, also known as bivariate normal, which I'll come to eventually. But for now, you are looking at a linear association, positive, and the scatter diagram is football shaped. We're just doing terminology here. Moving on down, what if it's nonlinear? Well, then here we are. It's like a snake. Nonlinear. You would certainly not want to fit a straight line through that, though it is astonishing how often people try. If you really want a term, how about heteroskedastic? Yeah, it's lovely. Hetero meaning different, skedastic means spread. If you look at this scatter diagram, it's skinny here, and then it spreads out here. So it has different spread in different parts of it, hence heteroskedastic. Not so easy to analyze these. Also, not so easy to analyze scatter diagrams that have outliers. An outlier is a point that's sort of very far away from the data in one sense or another. In this case, here's your outlier, and the bulk of the data are all the way down here. So it is several SDs away from the bulk of the data. In that sense, it is an outlier. Outliers can have a significant effect on how you interpret the relation between two variables. You have to be very careful what you do with them. People are tempted to drop them, but you know what? They're interesting points. And it's a good idea to go in and investigate why that point is so far out from the rest of the data. Maybe it's just a transcription error, in which case you can fix it. But if it's a genuine observation, then it might be worth seeing why that one is so different, and to make some kind of scientific decision about whether it should or should not be used in the analysis. That's one kind of outlier, which is quite far away from the bulk of the data. And here is another kind of outlier. So here, can you find the outlier? It took me a while. It's here. And why is it an outlier? Well, it's because the data sort of fit this pattern. They're going very close to a straight line. And then this fellow is just being a little different. Marching to its own drummer. Well, it's an outlier. So if I'm going to analyze the relationship, I can say, oh, it's beautifully linear. Not quite, because of this one. And we should examine that one separately to see why it is all the way out there. And so what has been the point of this section is mainly to get you to look at scatter diagrams, to see what you can see about associations, whether there is a sign to the association, positive or negative, whether the association is linear or not, whether there is an outlier or not. In the next section, we start quantifying some of the things that we have talked about.